It's been a very interesting day, and to cap it off, Ofer Aharony will lead the.
So this is supposed to be an open discussion on QCD strings. I'll start it out with an overview of what's known about QCD strings, and emphasizing the differences that I think are more promising, and so that will be like maybe 20 minutes, and then hopefully we'll have a free discussion of these issues.
So I think you know the while. Okay.
Just follow.
Yeah, it's just follow from this. But...
No, it will be just below.
Yeah, so I'll start with a 20-minute introduction to various aspects of QCD strings, and then we'll have a free discussion on these aspects and anything that's left over from the talks today and any other topics as well. So the big question is how to find the QCD string, and to be clear and what I mean by that. So we know already for almost 50 years that every large N-gauge theory is equivalent to some string theory with a string coupling constant scaling as 1 over n. So what I mean by finding the QCD string is just finding what is the worldsheet theory of this string theory. Of course, QCD strings do appear also at finite n. I mean, as we heard and we saw it in lattice simulations. I mean, but at finite n, these strings are not decoupled from other states. I mean, so they're of course very useful at low energies for low excitations with string, but they're not well defined at all energies where they start mixing with additional strings and glue balls and so on. While in the larger limit, this is really a clean problem of where a single string just decouples from everything else, and we can really ask what's the worldsheet theory of that string at all the energy scales. So that's what I mean by finding the QCD string. And we have a few examples that are known already of worldsheet theories for large N-gauge theories. So I guess the first example perhaps is an example found by Gross and Taylor for the two-dimensional Young-Mills theory. So in that case, Gross and Taylor wrote down some rules for how to formulate a string theory that reproduces 2D Young-Mills theory. And it's Wilson-line correlation functions. Now this worldsheet theory is, well, in the paper of Gross and Taylor, they didn't formulate it directly in terms of a local worldsheet theory, but rather in terms of rules for summing over worldsheets. And as far as I know, even 30 years later, the form of that worldsheet theory is not completely clear. I mean, so some things are known about it, but there's still no complete local worldsheet action that reproduces that expansion. But I mean, so in some sense, we know what the string theory is in this case, but there's still, I think, room for improvement in finding the precise worldsheet theory in that case. And then starting 25 years ago with the ADS-CFT correspondence, we have many examples of holographic backgrounds where we have string duals to various gauge theories. So in those cases, we know that in all these holographic examples, the string moves in some higher dimensional space-time that includes, in addition to the usual directions of space-time, it also includes at least one extra radial direction, so that the string moves not in the usual four-dimensional space, but in some warped space that has the usual four-dimensional space in it, and it also has some radial direction and perhaps some extra dimensions, depending on the precise details of the theory. And one characteristic of these examples is that this spacetime that the string moves in has a boundary, and insertions of local operators are described by perturbations at the boundary, and also insertions of Wilson lines are described by things happening at the boundary, while the string itself propagates in the bulk in the lower values of this radial direction in the space-time. So of course, the most famous example of this is the equivalence between the n equals four-dimensional super Young-Mills theory and type 2B string theory on ADS 5x5. So this is a conformal example, but we have also many additional examples of this also for non-conformal field theories, some of which were mentioned before. Now, these holographic examples are mostly understood in the limit where the curvature is small. So where the curvature of this space-time is small compared to the string scale. And so there are two things that become easier in this limit in which the curvature is small. One advantage of this limit is that the worldsheet theory becomes weakly coupled in that limit, as usual in string theory at low curvatures. We have weakly coupled worldsheet theories. And the other advantage is that in space-time in that limit, we can also approximate the theory just by gravity. And for many purposes, we can ignore the stringy aspects. So most of the results on holographic models are in this limit where the curvature is much smaller than the string scale. Of course, working in that limit has a big disadvantage that from the point of view of observables of QCD-like objects, then the scale of say, the global masses and other scales are typically fixed by the curvature scale. So working in this limit means that we're working in confining theories that have the property that the string tension is much larger than the scale of the mass gap squared and also the global mass squared. So being in that regime is necessarily very far from QCD-like theories where the tension is of the same order as the global masses. And in order to approach that, we have to get away from this limit. And of course, the problem with doing that is that then, well, the worldsheet theory generically would expect it to be strongly coupled in that case where the curvatures are not small. And also the space-time theory does not have any good gravity approximation. So obviously, we need better tools to study that in that limit. So I mean, so one thing that's presumably generic in that, well, so if we want to study theories where this, like QCD, where the string tension is of the same order as the global masses, then generally we expect this two-dimensional worldsheet theory to be strongly coupled. I mean, there's no small parameter to expand it in. So on one hand, one could say that maybe it's hopeless because we're replacing the hard problem of solving QCD by finding some two-dimensional theory that's strongly coupled. But of course, in 2 dimensions, we do have much better methods to deal with some strongly coupled theories. And I think that, or even if we would find just a 2-dimensional Lagrangian theory that would flow to the correct QCD string theory, I think that would already be very useful for at least answering some questions about the QCD string. So I think just the fact that it's described by 2-dimensional strongly coupled theory is not a reason to lose hope. So
strongly coupled on the curvature is large.
well, I mean, coupling over to 1. I mean, what I meant by strongly coupled is just couplings over to 1. So yeah, so of course, for the QCD worldsheet theory, I mean, we don't have any small parameters. So in these examples, there's always some small parameter that you can take to get to this limit and then expand in it. But for the QCD string on the worldsheet, I mean, once we've taken the larger limit, we don't have any other small parameters. So there's no reason to expect the theory to be weakly coupled. So in general, there are 2 types of approaches that can be used to study the QCD string theory. So we can generally divide them into bottom-up approaches and top-down approaches. And I'll review each of these in turn. So let's start from the bottom-up approaches. So the bottom-up approaches for confining theories, essentially, we already heard about them. So they involve looking at long strings. So we want to study some long string that has some typical length scale L, which is much larger than the typical scale, which would be the 1 over the square root of the string tension. And for these long string configurations in confining theories, we can perform an expansion in 1 over L squared times the string tension. Essentially, you can think of this as some sort of a derivative expansion on the worldsheet, because 1 over L is a typical variation scale for the fields on the worldsheet. The details of precisely which derivative expansion it is depends on which gauge choice you use to describe this worldsheet theory, but in any gauge, it's some sort of a derivative expansion. Now, on the worldsheet of the QCD string, we know that we always have the degrees of freedom of the embedding of this string in space-time, and that gives rise to, if we're looking at a string in d space-time dimensions, to d minus 2 massless scalars on the worldsheet corresponding to the broken translation invariances by this long string. And generically, we expect that these should be the only light degrees of freedom on the worldsheet of a long string. And so we expect to have the higher excitations coming in at an energy scale of the order of the string tension. So they should have a mass of the order of the string tension corresponding. And at that scale, we would start seeing various internal excitations of these flex tubes and any other additional degrees of freedom. Now, this is true if we don't have any extra symmetries that are broken by the string. Of course, in some examples, like in supersymmetry Higgs theory, where the string breaks supersymmetry, then we would have extra fermionic light fermions on the worldsheet and so on. And there are various other examples where the string breaks some symmetry, but if the string does not break any symmetry, then we expect these to be the only massless degrees of freedom. And then in this setup, we can write down the most general effective action describing these degrees of freedom. And typically, we write that in terms of the induced metric on the worldsheet. And in terms of the induced metric, as we heard already in previous talks today, we can write down a general derivative expansion for the worldsheet action that starts from the Nambu-Goto action. So we know that the general form of the action is the tension times the integral of just the Nambu-Goto action. Then there's this specific universal term proportional to 26 minus d that was described in some gauge choice in gauge choice, but it exists in any gauge choice. So this is a universal term that we can explicitly write down in any gauge choice. And then at a derivative order on the worldsheet, we start getting non-universal terms, which start with what looks like the curvature squared of this induced metric, and then there are various other terms. So this bottom-up expansion is well understood by now, and it's parameterized by these non-universal coefficients that start showing up at a derivative orders. And as we heard, the lattice simulations of these confining strings are starting to get to the level of accuracy where they could actually start measuring some of these parameters of this expansion. I mean, so up to now, they were mostly just confirming these universal terms and verifying that the form of the string excitations agree with these universal terms, but they're starting to become accurate enough to measure these coefficients. And in principle, well, at least the most naive thing that the lattice can teach us about QCD strings would be measuring these observables, which are the coefficients of all these terms just in the derivative expansion of the worldsheet action. So that's one obvious way that the lattice can teach us about QCD strings would be just to measure these coefficients more and more precisely. Now, of course, the big problem with this expansion is that we don't expect it to converge. I mean, so this expansion is useful for length scales that are much larger than the string scale, or for energies that are much of the excitations that are much smaller than the string tension. But we expect this type of expansion to break down once we get to energies of the order of the string scale. And in particular, that's certainly expected because we expect additional degrees of freedom on the worldsheet to live at that scale, which would correspond to any internal excitations of the flux tube or any other degrees of freedom. So it's not so clear how to use this bottom-up approach to really learn about the full QCD string theory rather than just giving us an expansion for these long strings. So a priori, one might think that this is completely hopeless because this expansion breaks down, and in any case, we expect the theory to be strongly coupled. So probably there's not much hope, but as we heard in Sergei's talk, and we'll hear in Victor's talk tomorrow, there is some glimmer of hope in taking this approach further, because there are indications from the lattice that perhaps this low energy theory is close to being an integrable theory, which a priori there's no reason for, but it just seems to come out of the lattice results. And if it's close to being integral, or if it would exhibit any other specific properties, then that may raise hopes of actually being able to extend it to all energy scales. So one bottom-up approach, which could be useful for going to high energies, would be to ask, and again, we'll hear more about this, I'm sure, tomorrow in Victor's talk, is to ask, are there integral models that arise from consistent string theories? So is there some string theory that is valid at all energy scales that gives for the, well, and that leads to an integral model when you take it, say, to the static gauge or to one of these gauge spaces and analyze the roll sheet scattering. Now, these consistent string theories, I mean, well, one hope could be that they're even dual to some specific gauge theories themselves, but even if they're not dual to gauge theories, I mean, even if they behave very differently at high energies, it would still be interesting to understand what these integrable models could be. And then the next step would be, can we analyze systematically the formations away from these integral points, and then get some, well, hopefully get to the actual string theory of QCD by some small deformation of those models. So that's I think the main hope for a bottom-up approach, being able to actually teach us something about the full QCD string world sheet. Yes.
So in your expansion, you're not writing down extrinsic curvature terms. You're grouping those in the higher terms at the.
Yeah. So in the context of this expansion, you can get rid of the extrinsic curvature scale because it's proportional to the equations of motion. So you can always get rid of it by some field redefinition. So that's so in this. So in this context, these are really the only terms that you have to write down. I mean, for
not if you have a k-squared term, though, right? I mean, the equation of motion has extrinsic curvature, but if you put k-squared in the action, you can't get rid of that by field reduction.
Well, you can't in the context of this low energy expansion. I mean, so of course, not for all field configurations, but in the context of expanding around a long string systematically, then order by order in that expansion, you can get rid of it. So in this context, you don't need it. I mean, yeah, of course, for the action at all scales, it may well be that you would start from actually writing it down, and that would maybe be more useful for all scales. So that I don't know, but just in this low energy expansion, you don't need it. Yeah.
It's present in vortex.
It is a photo. In principle, curvature.
Yeah. To higher powers, of course, you do have it. Yeah. This was just
But I mean, terms like that are actually important in classical vortices. There's an anti-rigid term in classical vortex.
Sure.
And then there's.
Yeah, sure. They may be useful for an all scales expansion. Just in this specific low energy expansion, you don't need.
This the string from n equal 4 super mills is integrable, right? That's known to be. At least they're long spinning string.
Yeah, so that's right. So of course, this expansion was for confining theories. I mean, it started around the string tension 10, but yeah, of course, we do know that the world sheet theory for some theories,
So
of course, is integral.
Theory like that, right?
Yeah, so I don't know any confining theory that looks like that.
There's not known like any examples of confining holographic backgrounds.
Yeah, none of them.
Integrable.
Yeah, I don't know any of them that are integrable, and right. But that would be in the top-down approach. So I'll get to that next. But yeah, from the bottom-up approach, that's not indicated. So the other possible approach to QCD strings would be starting from a top-down approach, which would use the fact that the gauge theories that we're interested in, I mean, in 2D and 3D and in 4D for asymptotically free theories, then we know that all these theories are free at high energies. And of course, the string theory should describe these theories at all energy scales. So instead of starting from these very low energy configurations of long strings, you could try to start from the opposite regime of trying to understand this string theory at very short distances or very high energies, and then view the gauge coupling if you wanted some deformation of that, and try to go from the top down. So if you want from the point of view of these holographic backgrounds, I mean, then typically they have some infrared cutoff scale coming from some properties of the geometry. So this bottom-up approach starts from analyzing these theories close to the IR wall and going up from there. Well, you could also imagine top-down approaches where you start at very high energies close to the UV region and then trying to go in the opposite direction. Of course, neither of these directions is obviously going to be simple, but these are sort of the two obvious starting points. And in this top-down approach, so you'd want to start down by writing down some string theory that's dual just to free gauge theories. And so that's not so easy to do even in this large limit. So for free gauge theories, I mean, so a typical state of the string in a free gauge theory, you can think of it as some single trace product of various products of field strength. I mean, so a typical state would look like some product of K field strength, say, with various derivatives acting on it. So in this limit where it's a free gauge theory, then these strings really don't look like continuous one-dimensional object, but they look more like some collection of string bits where each of these string bits is supposed to be one of these local gauge invariant operators. And then the trace just means that you put them together on a string in a specific cyclic ordering. But the string itself is really just a collection of these string bits, and that's also what's suggested by the 't Hooft expansion in this limit of free theories, where the finite graphs of the 't Hooft expansion just look like sort of ribbon graphs of individual gluons just propagating independently of each other. So in this limit, this QCD string theory should become a theory that is not really 1 plus 1 dimensional, but it's really a topological theory in the bulk. So there's really no degrees of freedom here in the string in general, but it should include the dynamical gluons as sort of string bits degrees of freedom that live on the world sheet somehow. So that's sort of on general grounds coming from the 't Hooft expansion. What we expect the string duals to free gauge theories to look like. And unfortunately, we don't understand these free string theories, which are the starting point for these top-down approaches, very well. So there has been some progress of this in the context of the n equals for supersymmetric Yang-Mills theory. So of course, this picture is valid in any free gauge theory. I mean, it doesn't really matter for in this free limit if you're talking about a QCD or about a conformal theory like n equals for super Yang-Mills. So in n equals 4 super Yang-Mills, there have been many efforts to study the string worldsheet theory, which in this case is just the type 2B string theory on ADS5 for SS5, in the limit where the 't Hooft coupling goes to 0, so that the curvature of the ADS5 for SS5 space becomes very large. So there have been various approaches to try to study this limit. I mean, starting from various formulations of the type 2B string. I mean, so there's a Green-Schwarz formulation, there's a pure spinner formulation, and there are various hybrid formulations and so on. And in each of these formulations, you can try to take this limit, but the results and so far do not seem very promising. And then there are some also newer approaches, some of which we'll hear about tomorrow from Matthias. So there's this Gabriel-Kamara approach, which is not directly related to the string theories with finite coupling, but starts directly by trying to write down a string dual for the free gauge theory. And hopefully, eventually, we will be able to write down explicit worldsheet actions that describe these free gauge theories. And of course, once we manage to do this, I mean, so for the free gauge theory, there isn't really any difference between n equals 4 super Yang-Mills theory or just pure Yang-Mills, or in 4 dimensions or in 3 dimensions. I mean, all of these free string theories should look very similar, just with sort of different letters sitting here at the different website, at the different these sites along the string worldsheet. So hopefully we will be able to understand by some combination of these approaches how to write down string theories for free gauge theories, and then one should be able to systematically deform those by the gauge coupling and use that as a starting point for understanding QCD strings. So this approach is in principle systematic as opposed to the bottom-up approaches. I mean, so if we find the string theory and find its deformation by the gauge coupling, it would certainly give us the QCD string theory. But both of these steps of finding the string dual to the free gauge theory and of deforming it are are not yet well understood. So let me just comment to end this introduction that you could also think of various other top-down approaches where instead of starting from the free gauge theory, you could also imagine top-down approaches where you start from some of the known string theory duals and then try to deform them to get to QCD. So for instance, one type of other top-down approach would be to start from the n equals for Mills theory and then say deform it by masses to all the adjoint particles so that you would flow to the pure Mills theory. So that would be another type of top-down approach that in principle should lead us to the QCD string. The problem with this approach is that if you try to add these mass deformations to the 40 n equals 4 Mills theory, then first of all, the theory that you get becomes a very complicated string theory, which is described by Polzinski-Strasser type backgrounds that are very complicated. And in addition, if you try to do these deformations in the limit where the 't Hooft coupling is very large, which is the limit where we understand this worldsheet theory best, then you find that the scale of this Young-Mills theory is of the same order as the scale of the mass deformation. So you cannot really decouple the QCD string for the other degrees of freedom. And in order to get a QCD scale that's much smaller than this mass of the deformation where the other degrees of freedom live, then you have to start with the 40 Young-Mills theory at very weak coupling so that you can get an exponentially large hierarchy of scales here. But then this goes back to this other problem of needing to understand the 40 n equals 4 theory at weak coupling. So it's not clear yet if this can be done. One other type of top-down example of this type, which I've been working on recently, is you can also start from the two-dimensional Young-Mills theory, where ostensibly we do understand what the dual string theory is, and you could then try to deform that by adding, say, massive adjoint particles, which when they're very heavy, they are well described by perturbation theory. So it should be possible also to describe that as some deformation of the worldsheet theory of the 2D Young-Mills string. And you can imagine also various other types of top-down approaches like this. So this was sort of a review of the method. Well, either one. I mean, should be possible, of course. I mean, so yeah. So each one of those should be some different type of deformation that you would add on the surface of these. So for 2D Young-Mills, the dual string theories would again be some sort of topological worldsheet theory, and then on top of that worldsheet theory, you should be able to add some additional particles on the worldsheet that would correspond to these adjoint fields, either scalars or fermions or both. And it should be possible to find a string theory that describes them. And so this case, in some sense, may be easier than these other cases because here, I mean, well, because it's 2 dimensions and we can solve many things, and also the worldsheet theory and also the spacetime theory here at lower energies does just reduce to pure Young-Mills, which again is a topological theory. So this case may well be the simplest case of finding a dynamical QCD-like theory, but again,
So
so far,
you're deforming
no,
the gross Taylor?
well, so yeah, you could try to deform that, but I mean, but yeah, you'd like to deform that by writing it as some local worldsheet theory. So you could start from some of these local worldsheet theories that were suggested to reproduce the gross Taylor expansion. I mean, so there's one approach by Petr Hajova, and then there's another one by Kurzmur and Ramgulam, and you can try to take these worldsheet theories and just add to them these extra massive particles, and so that should give you some theory that flows. So here it's sort of, I mean, so well, in the RG sense, this is sort of an opposite deformation. I mean, maybe this is more a bottom-up approach than a top-down approach in the sense that you're adding here massive particles and try to write down the string theory that would include these massive particles at higher energies, but it's well, it's top-down in the sense that, I mean, the starting point is, well, this is really a weakly coupled theory when the point of view of perturbation theory when these adjoints are massive. I mean, so in that sense, it's a top-down approach. So maybe this is some sort of hybrid top-down, bottom-up approach. Which
But what
maybe is
theory still strongly coupled at high energies, right? That's never.
well, probably, well, again, strongly coupled in the sense that it should reduce to one of these string bit models at high energies, because at high energies it is just a collection of these adjoints built into and because since you don't have dynamical gluons in this case, I mean, it is just some state of adjoints written up in the gauge right way. So it's maybe strongly coupled in some variables, but it should be weakly coupled in some other variables where it looks like that. And then in the middle, it's
Yeah, I'm trying to understand, because if I take long string, right? So because that's question about Scott, long string, it's not about approach bottom up or down, like what can ask, it's a physical question, right?
yes.
And if I look at the S matrix at high energies, well, there are always degrees of freedom. It's not that it's logical, right? So there will be some in the test matrix. So in what sense is weakly coupled? Because
yeah, so it, of course it will not be weakly coupled for long strings. I mean, so yeah, so I'm not saying that the effective theory on the long string will be weakly coupled. I mean, that always starts from this bottom-up approach with these other degrees of freedom, and in that language it will probably be strongly coupled. But again, there should be some other language where if you just look at these sort of global states that are made from a finite number of globals, and those should be described by some weakly coupled description that just reproduces the perturbative gauge theory. And then, yeah, of course, eventually, what we'd like to do is to interpolate between that regime and this low energy regime of the long strings, and there should be some QCD string theory.
no, but I'm not sure why you say it's low energy, right? Because then, okay, I'm asking take long string.
Yes.
We're asking what happens at high energies
Right.
on the long string.
Yeah, but
And that's not a weakly coupled theory.
that's right. Yeah. So as you described in your talk, in that case, there would be lots of soft particles that are emitted and so on, and so that is not a low energy process. But what should be low energy is just looking at these very high energies, global like states, which are just made out of these free particles, or but differently, just looking at the dual of the free gauge theory, which again, of course, in that case, you don't have any of these long strings, and this is just a free theory, not a confining theory. But once you deform it by the gauge coupling, then it should eventually flow in the infrared to something that will include also these long strings.
I thought that one hint from holography was that there is RR coupling.
Right. So yeah. So of course, yeah. So a question that I didn't discuss is precisely what form do these worldview theories take. So it's true that, I mean, when you start from the bottom up approach, then it looks like we're just building bosonic string theories. But on the other hand, what we know certainly from holography and from many other places is that the worldview theory cannot just be a bosonic theory, but it's probably going to be a superstring theory with Romanov backgrounds, because that's certainly what we see in all the holographic backgrounds, and that's probably required on general grounds, because we know that the theory is not supposed to have a tachyon. So
some kind of massive fermions of the world.
So in the confining holographic backgrounds, then you certainly see that in addition to all these massive fields, you always have massive fermions on the world sheet and so on, so that it is described by some superstring theory. And presumably also already to describe these free gauge theories, you will also need to add fermions on the world sheet. And
what does it mean for long strings? Because again, this example, 2D young music or some adjoint matter, we kind of understand the matter content. There is no, like, for instance, the scalar is a massive scalar. We understand bullshit theory. It will be adjoint scalar.
well, I don't think we understand it yet.
Well, but
in the
it's
first of
clear.
it.
There was one example of a model like this, which is well understood. So if you take just Yang-Mills in 2 dimensions with a mass, so give it an explicit mass term.
Okay.
Okay. So that model can be gauged to essentially a theory which is like what you have. And the spectrum of that is known for small Yang-Mills couple. So the elementary excitations are given by 2 scalar excitations, which are bound. And there's a phase shift as they pass through each other. The S matrix is known. And it's not everything is known about it. The high energy properties are not known, but the low-lying spectrums.
Okay. Yeah. So that could be an interesting kind of model for these games.
What's that?
Which theory are you talking about?
I'm just saying, if you take Yang-Mills and you put in a mass term,
What do you mean by
that's the unitary gauge formulation of a sigma model coupled to the gauge theory, the gauge sigma model. And for small gauge coupling, you can work out the spectrum of that model by a method similar to that of McCoy and Wu for the Ising model in a magnetic field. It's the same kind of problem.
It's not a gauge theory. You're adding tracing.
You can write it as a gauge theory. You can think of it as a gauge theory in a unitary gauge. So it becomes a theory of adjoint matter, scalar matter, coupled to gauge theory. And I'm just saying that the high energy spectrum, which would require a beta salpeter analysis, is not known, but the low energy spectrum, which can be studied by a McCoy-Wu type method, is known for NEN, for SUN for NEN.
One question that they asked a few times is whether this axion that we saw very convincing evidence for is somehow a composite state of world sheet fermions.
Yeah, so I think that if you want your string theory to be really be valid at all scales, then I think it necessarily must have world sheet fermions. I mean, if it's just a bosonic string, then one can prove that if the high energy spectrum, I mean, just includes bosonic states, then it would necessarily have a tachyon. I mean, so there's, I guess, Picasso and Seiberg proved various theories of that type that for standard strings, I mean, if your Hagedorn spectrum is not asymptotically supersymmetric, then you would necessarily have a tachyon. So I think you must have something like strings in a background to get around that theory. So presumably at some level, if you're trying to write down a microscopic formulation of that string that's valid at all energy scales, then it will necessarily have world sheet fermions, but it's not so. Yeah, so possibly that axion would be a bound state of those, but it's also possible that the fermions only show up at higher energies. So yeah, so it's hard to be.
Would that make a prediction that when you look at higher energies on this long string, let's say for numerical calculation, you should see these fermions?
Well, it's very difficult to say because those variables are probably strongly coupled on the world sheet. So it's hard to say how exactly you would see them. I mean, so I don't know how to make any sharp predictions from that. I mean, so we know that in some sense it should be there, but it's not clear. I mean, again, there could be other variables for this energy point of view, say where you don't explicitly say that, and then yeah. So I'm not sure how to make that more concrete.
Could show up as kinks, maybe.
Well, it's not obvious that sort of a single fermion state has to be in the spectrum, because often you have in these theories also whatever kappa symmetries and other things that project out some of the states, and that's how you can avoid all these theorems that modular invariance would necessitate a tachyon, exactly by having various constraints and projections and things like that. So it's hard to say. I mean, but yeah, possibly. I think we just don't know enough about those string theories.
Should this new axion particle that was discussed lead to some exotic mesons or things like that?
Well, again, this particle was only found for long strings.
No, but you expect, yeah, because basically expect if there is some highly excited hadronic state, you expect that there will be excitation which can be obtained by adding the particle on the world sheet. And actually, well, maybe we'll talk about Shahzad at some point. But we're looking at spectrum of 40 glue balls, and there is like the low line state is 0++, but there is low line excitations which is 0-+, which is very hard to interpret in any kind of string theory description, like just in terms of Bogota states. But on the other hand, that excitation. So basically, if I'm just naively take 0++ glue ball and add axion on the string, that would give 0-+ state. So indeed, the prediction would be that there should be basically hadrons should come up with pairs.
Yeah, so for high spin glue balls, that's definitely true because they would be long strings and they will be described by the same.
Have you seen this?
Well, on the lattice, we
But-
don't see.
Nature, so there are a bunch of high spin glue balls, right?
Well,
Not
glue
glue
balls
ball,
are not
mesons,
that-
sorry, mesons.
But for mesons, one expect, yeah, so for high spin
Yeah,
mesons.
so also for high spin
one
mesons, right?
expects
for the
that's
same
kind of
reasons.
prediction. Yeah, but it's a bit hard to make it it's hard to make it quantitative because naively one said, okay, just the mass gets shifted by the mass of the axion. But for instance, for mesons with light quarks, it's described kind of by rotating string. And then when one tries to do the calculation, if you add axion, sometimes there is centrifugal force which pushes it towards the end point of a string. And there, the end point is strongly coupled from the point of view of effective field theory. So actually, like there is a qualitative prediction that there should be pairs of state with basically split parity, but to turn it a quantitative prediction about mass difference, it's for higher quarks it's straightforward, but then it's Dirichlet boundary condition, but and that's what one sees in lattice simulation. But for actual mesons with or physical ones with non-zero momentum, that should be done, and I think it's possible to do, but it hasn't been done yet. Yeah, but that's definitely the expectation.
But if there were fermions in the world sheet, you'd also expect single fermions to affect closed string states in the same way, right? So it would be a different prediction. So you could test that idea. No?
But fermions, yeah, but I don't see.
Well, the suggestion was that the axion is about theta. That your term phi
Right.
k twiddle is really psi bar.
Right, but does one expect excitation with a single fermion?
Yeah, it's not obvious. There should be an excitation with a single fermion. I mean, there may well be some projection that projects out there may well be some projection that projects out all the states which have the odd fermion number or something like that, which typically happens in these string backgrounds.
Like in type 0 theory, right? We project out all fermionic.
For example.
Yeah.
Yeah, so is it possible to translate, I understand this kind of expectation, because you call it bottom up and top down, but it's mixing a little bit. For me, I wouldn't call studying log strings as like bottom up and top down. It's a kind of clearly well-defined physical question. That is scattering on a long string, and there is a physical observable S matrix or fine volume spectrum, and kind of here you talk about more serial like of closed short strings, right? When you say about this weakly coupled description, and that's in that language one expects to have bullshit fermions. But is there sharp prediction from that expectation to what one sees for long strings?
No, I don't think so. But again, I think the way I think about this distinction is from the point of view of these holographic backgrounds. I mean, so there we certainly do have some. I mean, there is some UV boundary and there is some IR region and the long strings are set here, and yeah, and even when you do some scattering on them, then probably even when you scatter at high energies, it's not like you go to the UV region. I mean, you're still staying here in this IR region. So from the point of view of the QCD world sheet theory, that you're studying the region of that sigma model that's close to here. All these top-down approaches would start from understanding really the region that's close to here, that say a string that was ascribed some correlation function that's for a distance of some trace of squared operators or whatever. So that would certainly be a string that just lives in this region of space-time. And there should be some string theory that reproduces these correlation functions. And then the full QCD string is really describes this full sigma model, I mean, including all of these regions and the interpolation between them. And yeah, so presumably by understanding better both the UV region and the IR region, and eventually we'll be able to interpolate between them and find the full QCD string theory. I think just starting from one of these ends definitely will probably not have enough information, so we should really try to go from both directions. But yeah, so in this context, I think there's a clear distinction between what I call the bottom-up and the top-down approach. I mean, so yes, it's not necessarily the slower high energies, but it's really whether in these holographic backgrounds you're staying close to the IR region or close to the UV region. So even when the background is highly curved, I mean, so there's not necessarily a clear geometry, then there should still be some sort of radial direction and some distinction between these regions. And so that's what I meant by bottom-up and top-down.
There's one simple example, which is this theory with a massive joint fermions with a mass tuned near the supersymmetric point. And then on the confining string, you just have a massless fermion, one equal one half theory. So that may be integrable. I don't know. It's not known.
Right. Yeah. So is it?
Coupled to
Free-
gauge field?
Well, a joint fermion coupled to gauge field.
Free adjoint fermions.
Well, they're not free after they're coupled.
They're close to them.
Yeah. No other term. I think it's known that there is special mass where the theory is supersymmetry as a kind of accidental super. And in that case, actually Sergei pointed out that on the long confining string there is exactly massless, which can be scattered.
Yeah. So that could give a. But is that true at all energy scales, or just the lower energies? I mean,
Yeah, it's not known what the spectrum.
yeah, because the high energies it still connects someone to perturbation theory. I mean, so it's not clear. I mean, at least for
It's
some
you're saying
objects.
it's still strongly coupled.
Yeah. I think important point, when you mean strongly coupled, again, because these S metrics, if you ask about S metrics for long string, then, well, we clip out coupled. Well, it's always strongly coupled, it's high energy. But actually, is that something which can be done on the lattice? Because basically that theory just, can one do what Andreas does for that series? It involves fermions, but on the other hand, it's 1 + 1D. So can one just study it?
I think it's generally hard to put just a single adjoint Meyer on the lattice, but
Yeah, that's right.
it may be possible.
Well, I think it's possible.
Well, yeah, you could probably use overlap.
Yeah.
I mean, it's not trivial, by any means, but is there an obstruction that you're aware of?
And one will need to tune to the supersymmetric line.
That's the challenge, yeah.
That's a challenge, yeah. But in principle, yeah, this is something that can be investigated.
Yeah, I don't think there's supposed to be a sign problem with the clock in this example. So that suggests that you can probably do it, at least in principle.
More suggestions.
Can I ask about your string bits? Are you talking about this whole idea of Charles Thorne, where somehow the gluons line up and they somehow the effective energy becomes that of a string?
No, I mean here I'm really talking about the free gauge theory. I mean, so there's no energy. I mean, so for instance, you could just think. I mean, well, one simple context is to think of say the free gauge theory on a three sphere. I mean, so there are the states are just in one-to-one correspondence with the operators of the free gauge theory, and then you just have these operators, and I mean their energy is just given by the energy of these bits themselves. I mean, there's really these lines connecting them. I mean, are just in our imagination, if you want. I mean, there's no dynamics into these lines. I mean, there's just a connection that determines the cyclic ordering of these states.
But you're not talking about n = 4, you're talking about pure angles.
Well, it's true in any free gauge theory. So it could be the free n = 4 theory, or it could be free 2D theory with adjoints. I mean, again, this is true for any free gauge theory. So in any free gauge theory, there should be some picture where it's just given by these string bits, which are just the free gluons. I mean, with no interactions between them.
I'm not sure what a free gauge theory is. I mean, once you take the coupling to 0, it's
Yeah.
basically a billion.
No, it's not abelian. I mean, well, we still have a non-abelian Gauss law constraint. I mean, that reduces your states to just these traces of products of gauge invariant operators. But yeah, otherwise it's free in the sense that the energy of the state is just the sum of.
Okay,
of
but
its
the only
scaling dimensions.
bit of non-abelianness in the whole thing is Gauss.
Exactly. Yeah. So that's, I mean, that is what you get in the free limit of these gauge theories. I mean, and so that string theory should reproduce, even in the QCD string, it should correctly reproduce the correlation functions of various operators at short distances and Wilson loops at short distances and so on. So it's, and so whatever this free gauge theory is, it should be able to reproduce all of these properties. And so in that sense, it should also have some hint of this radial direction. I mean, which it's not so clear.
It's a bit subtle, right? Because kind of when you the thing you said in the very beginning, kind of what we understand by QCD string, okay, we're taking Lagrangian limit.
Yes.
But there is order of limits here, right? Because when what we mean by Hopf limit, we take NC to infinity limit, keeping lambda QCD fixed.
Yes. That's fixed, but it could be zero also.
Well, I think
Yeah. Okay. Yeah. I mean, you're right that it doesn't go to the limit of. Yeah. I mean.
So basically, yeah. So
if in the UV scale you take it fixed to be any non-zero value, then of course you would always have some QCD scale generated. But if it's fixed at zero, then you would just get this free gauge theory.
Keep lambda QCD fixed, take planar limit. And then
right.
That's the kind of what I was talking about. Take the bullshit theory and consider Heine asymptotics of that bullshit theory.
Right.
And it's not clear. And what you call these free strings, that's the opening. You first take lambda QCD to zero.
Well, not necessarily, but you could also take lambda QCD fixed and just take very short distances compared to that. I mean, so you could just look at correlation functions or Wilson lines at very short distances compared to lambda QCD, and they would also be described by this free string theory in that limit. I mean, so it's, I think there's no problem with taking the large N limit. I mean, all these things do commute with the large N limit, but yeah, you have to just take very, very short distances compared to the QCD scale. And
you could put the theory on a 3-sphere, and then the coupling, small coupling, becomes totally physical. It's just coming because lambda QCD times R.
right.
Would anomalous dimensions matter? I mean, could you get logarithms somehow out of your nearly free string?
Well, not in the free theory, but of course, once you add the gauge coupling deformation, then of course all these things would show up definitely. And yeah, but I mean, of course, we'll hear more tomorrow from Matthias about how to formulate these free gauge theories, and then the next step would be to deform them, and then you would certainly need to address all these issues. But even formulating the free gauge theories seems to be hard enough. So we can start from that. And so one interesting question is where else can the lattice help us in finding the QCD string? I mean, so of course the easier thing for the lattice is to study these long strings and then extract those coefficients. But that's obviously very useful from the point of view of this bottom-up approach. But it's not so clear how from the lattice you could extract what the string looks like in these other regions. I mean, of space. I mean, certainly at these very short distances or here. So it would be interesting to have some ideas for how the lattice could help us also to study some of the strings in these other regimes. So,
well, but it's more the question: what is a sharply defined observable which probes that physics? Right?
Right. Yeah.
Because on lattice,
that's
there
right.
is this matrix on one string which is fight at all energies. So in that sense, it's bottom up. It's not bottom up.
Yeah.
Up, bottom down. It's kind of just well-defined observable. But there is a spectrum of short, like blue balls, which is spectrum of short strings.
Certainly will.
But
how do you compare that with some?
But how from that spectrum, how to go from there to bullshit theory? That's
really hard.
right.
But well, but of course there are many other observables as well. You could just study some small circular Wilson line and so on, and then try to relate that to some string action in these spaces. And you could study correlation functions of local operators in Wills theory. I mean, those are also good observables, of course, and it's more difficult to translate them to the string language, but in principle it should also be possible. So thinking about these observables on the long strings, I mean, that teaches us about some corner of this QCD string space, which is this IR region, which of course is very interesting, but I think maybe we have to think also about other observables to enable us to find the full QCD world theory. And yeah, of course, it's very hard to formulate them in a in a diffeomorphism invariant way on the world sheet and so on to extract what's the essential physics. But I think that's one challenge that we should face.
But I'm not sure why you call it IR, because again, studies scattering.
Yeah, again, I was just in the sense of this radial direction and holography.
But still,
again,
when
that's
you
how
start
we-
to study high energy scattering on the long
Yeah.
string,
Yeah.
then it kind of wiggles. High energy excitation corresponds to kind of large amplitude in constant hypergalactic direction. So that S matrix knows about the UV as a geometry, right?
No, I don't think so. I mean, I think it's, as you said, it was for instance some zigzag here. I mean, and it stays here. I mean, I don't think just going to higher energies would necessarily take you far away in the radial direction. I mean, it's not, at least it's not obvious why it would.
Well, if you consider high energy excitation, that means it's now wiggles.
Yeah, of course. Yeah, but that's a different thing than high energy scattering. I mean, so you're about low energy high scattering emitted with a high center of mass energy. So there, I'm not sure.
No, why? Because it's kind of.
Is this Reggie versus Bjorking's limits? I mean, in one
No,
case, you're talking about fixed resolution, but very high energy. So
Well, because the theory is like, I imagine scattering just the translational modes, even that, right? Because the bullshit theory is not integrable, right? So so if you start from scattering, it has a large amplitude in kind of in non-holographic direction, but as a result of scattering, it gets excited in the radial direction. So
well, but
it's not
obvious that you get excited in a way that really takes you over there. Of course, you excite many soft modes of the excitation corresponding to this direction, but it's not obvious that your string really would extend significantly away in that direction. So again, of course, there should be some excitations of the string that do take you far off in this direction, but it's very difficult to identify those.
Because I can't just by hand, I can start with a long string, but excited that way that it sits asymptotically sits on the IR and then goes in the middle, deep in the UV region, and then comes back on the IR mode.
Yeah,
and that's a physical state of a string. And if you wait,
but it's probably not a very
into some.
But it's probably a highly non-generic state. I mean, so it's not obvious that state would be the one that would be formed by
it's
by
not generic,
collisions.
so it may be hard to extract the physics from the S matrix, but that information principle, it is.
Oh yeah, sure. Yeah. So if you want, that could be one interesting question for the lattice would be how to identify these states that really stretch out in the radial direction as opposed to just generic string states. So yeah, that's one way maybe to formulate that question. Yes. And of course, in particular, well, one way to try to answer that question would be precisely to compute, to look, say, in a background of a long string, but in that background to insert some local operators. I mean, like on top of that background to insert some correlation function of trace of square root of x in the background of some long string. I mean, so there we do know that the string is supposed to extend all the way there and go back down. I mean, so studying local correlation functions in the background of long strings could be one way to try to interpolate between these two limits. And that's something that has not yet been looked at all.
Measuring the profile, the transverse profile of the string.
Right. So from the point of view of the string, so living in the four-dimensional space, it attracts that. But yeah, but one should be able to translate that somehow also to some profile in the radial direction, based on our experience in confining backgrounds holographically based. So.
So certainly can study for QCD with some number of adjoints. I mean, this like the one adjoint is supersymmetric. Maybe look for what if one of these is integrable.
Yeah, well, of course, yeah. Having any integrable example that makes sense at all energy scales would, of course, be a huge breakthrough here because it would really give us a model where we can make all these things very explicit. But yeah, we're still not there yet.
But that we kind of know, right? Because to get integrability, we need to get enough long massless states on the string. Because this relation of integrability comes from this D-26.
So you're saying that if you add massless fermions on the string, it's good for.
Well, you need to add sufficiently many of them, but that's exactly.
But then
there is numerology that coefficient. Actually, it's exactly one with beta function coefficient. That's why n=4 is not integrable. It's from that point of view, but it's really kind of, it looks like integrability is related to non-conformality. That you need to add enough matter such that by counting it becomes conformal, but then of course, then you lose confinement. right? So
Yeah, but I mean, generic matter fields would give you massless degrees of freedom on the string world sheet. I mean, for that, you really need to have some extra goldstones and so on. So you really want to add some extra symmetries that are broken, and then maybe you could try to get to that regime where you're effectively in a critical string. Yeah. That's another interesting direction. Definitely.
So, may I suggest something?
Sure.
I mean, in the lattice community, there are several, studies of like theories that they move towards the conformal window, for instance. So there are all sorts of different theories with adjoint fermions as well. So it would be nice to know of this, what these theories are, and whether we can, get something meaningful out of all these theories. For instance, we are simulating SU2 with one joint fermion.
Mhm.
Okay, so I think this could be used. In this
I mean, for a massless fermion, I mean, when it's supersymmetric or away from.
No, but we can drive the theory towards
Right.
very small masses.
Mhm.
And this is something we're planning to do to calculate like flux tubes in this.
Mhm.
In this
Right, so it's possible that, I mean, so if you are studying it in the supersymmetric case, then the Lorentz theory would include also these fermions, and perhaps that would increase your chances of being integrable. Again, we don't understand the reasons for why these Lorentz theories are integrable, so it's hard to say anything, but certainly studying them in any other example, and in particular in supersymmetric examples, may be useful just to see if this integrability is an accident for 4D angles and 3D angles, or does it happen also in the theories with adjoint fermions? I mean, does it happen in supersymmetric cases? I mean, I think all these questions are completely open, and any input from the lattice would be very welcome, definitely.
Okay, well, I think it's been a very productive day, and let's thank Ofer for a very